Hi scholars, welcome back to Primar's Classroom. I'm popularly known as Dr. Sodium. The purpose of this video is to help you to cover the entire syllabus in chemistry. And this is the second topic of the syllabus, atomic structure. Now, when you're studying atomic structure, you have to take your time to understand some concepts in chemistry. Now, at the end of this class, you should be able to teach your younger ones or teach your friends about this topic. That will make it stick better and that will make you to understand it clearly. So let's take our time to understand atomic structure. So what are the things we're going to cover in this class? I'm going to introduce you to atoms. So we'll look at the introduction to the atom, the structure of the atom, the composition of that structure of the atom. Then after the introduction, we'll look at what we call the subatomic particles. I give you the properties of these subatomic particles. Then after that, we'll look at the history of the development of the atoms. We call it the atomic model. We talk about the different scientists that worked on the structure of the atom. Then when we are through with all of the scientists and their discovery and everything they've done, I will talk about that briefly in order not to waste time because we have a whole lot to learn on atomic structure. Then after that, we'll talk about all of the terms you use when you're talking about the atoms. So there are a lot of terms you'll be hearing here and there. Pay close attention so that you understand these terms one after the other, and I will give various examples. Then after talking about these terms, we're now going to look at the quantum numbers. The quantum numbers, they are the 4 quantum numbers, and I'm going to give you some calculations on the quantum numbers so that you understand this once and for all. And when you get to universities, these are going to be useful for you when you get there. Then finally, I'm going to talk about the rules that guide electronic configuration. Now, at the end of the day, go to the street, call everybody together, start teaching them atomic structure. So let's get started. The first thing you want to know is the definition of the atom. In the previous class, I told you something. I said when you break down everything around you, take the shirts, this marker, even the humans, everything around you, when you break it down to the smallest piece is called the atom. And we define then that atom is the smallest part of an element that can take part in a chemical reaction. So the smallest part of matter is atom. There are still theories that say there are smaller particles, but that is not the purpose of this class. The purpose of this class is for you to understand that the smallest part of matter is atom. Now, when we talk about atom has this structure. Now, in the structure of the atom, the circular part that you are seeing is usually called the orbit, or called the electronic shell, or called the energy level. It is represented as N. So that circular part, you can call it orbit, energy level, or electronic shells. Now, around that orbit is where you have the electrons. So the electrons are assumed to move around that orbit. Then deep within this atom, we have what we call the nucleus. The nucleus is the center of the atom, just like when you say nucleus is the center of everything. So the nucleus is the center of the atom. And inside this nucleus, you have some particles. Those particles are called protons and neutrons. I'm going to tell you about their properties. Just let's go on step by step. So they are called protons and neutrons. So if I ask you, where do you have protons and neutrons? Protons and neutrons are found in the nucleus of an atom, while electrons are found around the electronic shell. We want to study this structure and see the way things are built for an atom. Now, when you are talking about atom, we can't continue to draw these structures here and there. We should have a way to represent it. An atom is usually represented with a symbol X. Now, the top part of the A is usually called the atomic mass or the mass number, while the Z part is usually called the atomic number. Note that atomic number is what determines. You remember I told you to learn the first 30 elements in the previous class, and I gave you those 30 elements from hydrogen to zinc. There is a position you see that hydrogen is at number 1, meaning that the atomic number for hydrogen is 1. So the position of the elements on the periodic table is what the atomic number represents. So when you're talking about the atomic number, that is the Z, and that is also known as the number of protons that the atom has. So Z represents, for example, look at carbon. The atomic number is 6, the mass number is 12. So that is how you categorize it. And inside the nucleus is where you have the mass number. The number of protons plus the number of neutrons. It is called the mass number. So now, after talking about the representation of atom, so look at these various elements: oxygen, sodium, and magnesium. Can you tell the atomic number? Can you tell the mass number? You can leave it in the comment section. So let's move on. Now, so if we had said it that atom is the smallest part of an element, do you think that theory is true? We're going to be looking at a whole lot of things as we move on with the class. Atom being the smallest is still made up of some atomic particles. Atom itself still has some things that make up the atom. These things that make up the atom, they are called the subatomic particles. So if they ask you what are the subatomic particles, just remember pen. The subatomic particles are protons, electrons, and neutrons. Those are the subatomic particles. That means that these are the particles that make up the atom itself. So now let's look at the properties of these subatomic particles, because you hear here and there protons are positive, electrons are negative, neutrons are neutral. So looking at the table given, now you need to know, they can ask you for the charge of a proton, they can ask you for where can you find a proton, they can ask you for where can you find electron, where can you find neutron, what is the mass. Like there was one exam I did, they never gave me mass of the electron, and they said I should do some calculations. So you have to know this mass offhand too. When the time requires, you're going to be applying them. So now the mass of an electron, if you look at proton is positively charged, electron is negatively charged, while neutron is neutral. Now when you're talking about the masses of these subatomic particles, the mass of a proton is 1.67 times 10 raised power minus 27. The mass of neutron is 1.68 times 10 raised power minus 27. That's in kilogram. While the mass of electron is 9.11 times 10 raised power minus 31 in kilogram. But they can ask you what is the mass in atomic mass unit. That's another unit we just used to represent the mass. The mass of a proton is 1 in atomic mass unit. That of neutron is also 1. And that of electron is 1 over 1840 times the mass of proton. What does that mean? Electron is very, very small compared to proton. So if they ask you, the mass of electron is very, very, very tiny, very small compared to the mass of proton. So that is what we are saying. Now, let me ask you again, where is proton located? Where is electron located? Where is neutron located? So protons and neutrons are found in the nucleus, while electron is found around the shell, or what you call the orbit. Those are the subatomic particles. So let's move on to the next thing. The brief thing I want to quickly talk about is the historical development of the atom, or what we call the atomic model. Now, when you're talking about the atomic model, there are a lot of scientists that work on the atom, and there have been a lot of controversial statements concerning the development of the atom. You didn't just come and just see electron, proton, neutron, and we start talking about them. Some scientists had already worked on all of these things before we started talking about them. So the first thing I want you to know is the scientists that told us everything about atom. Although there was a philosopher called Democritus, he told us that if you divide everything in this universe, the smallest you have is called atomos, meaning atom. But he gave it as a philosophy, and that theory was not really accepted totally because there was no experiment to back his theories up. He just gave it as an assumption, so to say. So, but someone came later, and the person is called John Dalton. So John Dalton talked about the structure of the atom. So John Dalton was the one that now told us a whole lot of things about the atom. John Dalton says that all matter are made up of atom. Everything you have in the universe is made up of atom. And he says atoms of the same elements are exactly alike in every aspect. Now, as we move on, you will see that most of these theories given by John Dalton was not true. Don't forget to write. Most of the theories given by John Dalton were not true. The theories were proved wrong by some other scientists. So we're going to talk about all the theories that proved them wrong. So let's do it this way. The theory given by John Dalton, what was the theory that proved it wrong? I already said that John Dalton says that all matter are made up of atoms. Yes, but he now said that these atoms are indivisible. That was what he said. That means atom is the smallest and you cannot break down the atom into smaller parts. But later, what did we say? That the atom is made up of some small particles, which we call the subatomic particles. And these subatomic particles are your protons, neutrons, and electrons. So in our own days now, we believe that atoms are divisible. The second theory was that John Dalton says that atoms of the same element are exactly alike in every aspect, meaning that atoms of the same element. So what he was talking about there is that like this: chlorine is an atom. The mass number of chlorine is 35. The atomic number of chlorine is 17. Now look at this also. This is also chlorine. This is 37 and this is 17. We call these isotopes. I'm going to get there as we're moving on. Now, this chlorine is of the same atom, but the masses are different. The mass number here and the mass number here is different, but the atomic numbers are the same. But John Dalton says that this element and this element are the same, irrespective of what you do. But this statement is wrong, because one is lighter, one is heavier. And the heavier one, we have a physical properties that is slightly different from that of this other element. So which means that atoms of the same element are not exactly alike in every aspect. So that is another theory. The discovery of isotopes proved that wrong. You know, when he gave his theory, there were a lot of concerns and everything, but the later discovery of the isotope proved that wrong, even though the theory was accepted in those days. But when isotopes were discovered, that proved it wrong. We're going to know what isotope is in case this is your first time in class. So we'll be defining what isotopes and the terms used in describing the structure of the atom. So the next person that worked on the atom is the person that discovered the electron. So the electron you're looking at there was discovered by J.J. Thomson. He called it cathode ray. So J.J. Thomson performed the cathode ray tube experiment to discover what he called the cathode ray, and which is now called electron. And in the cathode ray tube experiment, he gave some postulates, and he was also able to discover what we call the charge to mass ratio of an electron. I'm trying to take this slowly so that you understand the concept clearly, but I'm not explaining the experiment. I am still going to explain the experiments one after the other with time. So just follow the class through. Now, after J.J. Thomson, someone discovered the proton. Although for now, if they ask you in JAM, you can do, if you see J.J. Thomson, you can pick him for discovering proton. If you see Ernest Rutherford, for now, if you see Ernest Rutherford, when they ask you about who discovered proton, you can pick Ernest Rutherford. There's someone called Eugene Goldstein. Eugene Goldstein did an experiment where he used a discharge tube with a perforated cathode, and he placed the cathode at the center of the discharge tube to discover the proton, which he called the anode rays. Then there are a lot of things to talk about this, but in order not to waste time, let's just note those things I've said. So if they ask you who discovered the electron, that is J.J. Thomson. Which experiment did he perform? He performed the cathode ray tube experiment. Who discovered proton? Ernest Rutherford. Ernest Rutherford was given the credit for the discovery of proton, but we knew that the experiment that led to the discovery of the proton was performed by Eugene Goldstein. So if they ask you anything about Eugene Goldstein or the discovery of proton, you should be able to state that. So what did Ernest Rutherford now do? We have talked about someone that discovered the electron and the person that discovered the proton. So what did Ernest Rutherford do? Ernest Rutherford discovered what we call a positively charged nucleus. The experiment he did was that he bombarded a gold foil with alpha particles, and he discovered a positively charged core, and that is called the nucleus. So today we're able to talk about nucleus. Thank you to Ernest Rutherford. So what are you going to discover today? I know you are thinking that what will I discover too? I discover you, and I'm teaching you right now. So the next person we want to talk about is James Chadwick. We have been talking about neutron, that neutron is found in the nucleus. The person that discovered the neutron is called James Chadwick. So James Chadwick bombarded beryllium sheets with alpha particles, and he was able to discover the neutron. The next person to talk about is Robert Andrew Millikan. Robert Andrew Millikan discovered the charge of an electron. Don't get this wrong. If they ask you who discovered the charge to mass ratio, that is J.J. Thomson. But if they ask you who discovered the charge of an electron, that is Robert Millikan. Robert Andrew Millikan discovered the charge of an electron. And later there is a scientist called Nebor. Nebor made us to know that electrons are quantized. They are found at a particular energy level around the nucleus. Many of these theories were false and a whole lot of limitations, but we're still going to spend our time to understand the limitations about each theory talked about by each of the scientists. But for now, in order not to bore us or waste our time due to the exam, that's why we're talking about the important aspects that has to do with it. So most times, according to Nebor, electrons can be at the lower energy state and can be at the higher energy state. When electron wants to move from lower energy to higher energy, it will need more energy. So it has to absorb energy and jump to the higher energy. The electron can also go from higher energy to lower energy. So there is a particular state electron can occupy if it has the energy. So when it moves from high energy to lower energy, it emits radiation. And those are the colors we see for different spectrum. We're going to talk about that later, so don't get too bothered. So now let's carefully look at all of the terms that we use when we're talking about atom. We have defined an atom. An atom is the smallest part of an element that can take part in a chemical reaction and still retain the properties of that element itself. So the next term they can ask you is atomic number. Atomic number is defined as the number of protons in the nucleus. That is atomic number, and that determines the position of the element on the periodic table. The next thing is the mass number. What is the mass number? The mass number is the total number of electron plus the number of neutron you have in the nucleus. That is the mass number. So it can be given mass number M sub n is given as number of proton plus number of neutron that is found in the nucleus. So if this is the mass number, that means that if the mass number is 35, atomic number, which is number of proton, is 17, I can determine the number of neutron. And in this case now, the number of neutron is going to be 18 for this chlorine atom. What would be the number of neutron for this? That's going to be 20. So the mass number is what is indicated here. This is the number of proton or the atomic number. And from there, you can get the number of neutron using this formula. So from what I've said here, you can try and complete the table below, fill the gap, determine the mass number, the number of protons, just complete the table to see if you have understood what I've said here. So the next term is the nucleus. Now, when you're talking about the nucleus is defined as the center of the atom, where you have the protons and the neutrons. That's the center of the atom. Then there's a term called the nucleons. Nucleons is talking about we have protons and neutrons in the nucleus, but instead of saying protons and neutrons over and over, so those protons and neutrons are collectively called nucleons. So a collective term for the protons and neutrons in the nucleus, or for the particles in the nucleus, is called nucleons. Do you get that? So the next term to look at is aeons. So how do you define an aeon? An aeon is an atom that has either lost or gained an electron to become charged. An atom has lost electron or gained electron to become charged. When an atom loses electron, it becomes positively charged. That's why when you are the type that love to give, you are always happy because you give. So giving makes you happy. When an atom also gives electron, it becomes positively happy. So it's glad that, oh, I just gave electron. But when an atom gains electron, it becomes negatively charged. Now, negatively charged atoms are called anions. Positively charged atoms are called cations. So you have to understand that. So examples of positively charged cations and examples of negatively charged anions. When you have group of atoms that carry a charge, we call them radicals. So group of atoms that carry a common charge, they are called radicals. So now let's move on to understand more about aeons. I said something at the beginning. We have an atom that is neutral. Note this point, is very important, and I'm going to give you a question on this. So let's look at something. When you have an atom in the neutral state, this atom is neutral. one thing you will notice is that the atomic number will be equal to the number of proton, and that will be equal to the number of electron. Note this: when an atom is neutral, atomic number is equal to number of proton equals to number of electron. For example, if I say this is chlorine 1735, what is the atomic number of this element? The atomic number is 17. What is the number of proton of this element? It is also 17. What is the number of electron? Because it is neutral, it's not carrying a charge, it is also 17. Note that. But when an atom is charged, that means the atom has either lost or gained electron. Let me give you an example of the one that is positively charged and the one that is negatively charged. This one that is positively charged, the atomic number for this is 13. The mass number for this is 27. This is 8 and this is 16. Looking at these two ions, this plus 3 means this guy has lost 3 electrons. This minus 2 means the number of electron loss is what this will indicate. So if it's indicating plus 1, that means it has lost 1 electron. If it indicates plus 2, you can see here it's not indicating anything. That means it has neither lost nor gain. So if it's indicating plus 2, it has lost 2 electrons. If it indicates plus 3, it has lost 3. Same thing here. If it indicates minus 2, it means it has gained 2 electron. So the ones that gain are usually negative. So if you are the type that loves to beg, bring and bring and bring, most times you don't really have anything. But people that give, they are the ones that God bless the more. So now looking at what we have here, I have Al3 plus. If I now ask you that what is the atomic number for this guy, the atomic number remains the same. It is 13. It does not change. If I say what is the number of proton, the number of proton too does not change. What have changed is the number of electron. So when an atom is charged, atomic number is equal to number of proton, but no longer equal to number of electron. You have to note that point. So what is the number of electron of this guy? It has lost 3. So out of 13, it has lost 3. Then that means the number of electron is 10. This is very important. Now look at this. What is the atomic number? Atomic number is 8. Number of proton is also 8. But what do you think the number of electron is? Very good. It has gained 2 more electrons. Then that means the number of electron is going to be 10. Can you see the differences? Now you have to take note of this part. So quickly, can you determine the atomic number for this element, the number of protons and the number of electrons? Also F minus. So this is sulfur, this is fluorine. Determine for Mg2 plus and determine for Ca2 plus. So determine the atomic number, the number of protons and the number of electrons, and leave it in the comment section. So let's move on. So let's talk about those terms that has to do with iso. Every time you hear the word iso, it usually means the same. If you have watched our biology series, you would have seen that I talked about isotonic, meaning that the same composition, the same concentration in and outside itself. So if you're hearing isotopes, isobars, isoelectronics, isotones, they are all talking about the same kind of thing. So let's look at it. The first one we talk about is isotopes, which is a statement most of us are used to. But if you're just learning chemistry, just carefully listen. What we mean by isotope is an element or a nuclei that has the same atomic number but different number of neutrons. So isotopes usually have the same atomic number but different mass number. And this difference in masses is due to their number of neutrons. You remember when I talked about chlorine 37 and chlorine 35 the other time. Now look at this. So chlorine 35 has atomic number 17. Chlorine 37 has atomic number 17. What is the number of neutron for this? The number of neutron for this is 20. The number of neutron for this is 18. So what do you notice? They have the same atomic number but different mass number. Why do you think their masses are different? Because their number of neutrons are what? Different. That's why. Do you understand that? So isotopes are nuclides of the same element with the same atomic number but different mass number. So that's what we call an isotope. So let's look at what we mean by isotones. Isotones are nuclides of different elements with the same number of neutrons. Isotones, same neutrons. So when they have the same number of neutrons, you call them isotones. So look at examples of carbon 14, nitrogen 15, and oxygen 16. Determine their number of neutrons. You will see that all of them we have number of neutrons to be equal to 8. So they have the same number of neutrons, but they are different elements with different masses, with different atomic number, but their number of neutrons is the same. So we call them isotones. The next one we call is isobars. Isobars are nuclide with the same mass number from the word bar. So they carry the same bar. So with the same mass number. And example is argon 40, potassium 40, and calcium 40. So they all have the same mass number. So anytime you hear the word isobar, you're talking about nuclides with the same mass number. Is that taken? So let's look at isoelectronics. From the word isoelectronics, what do you think that is talking about? It's talking about nuclides with the same number of electrons. Is that taken? So there are elements with the same number of electrons. It can be elements, it can be ions. They all have the same number of electrons. So they are called isoelectronics. For example, so check these ones out. K plus, S2 minus, Cl minus, and Ca2 plus. For these ions that you have, determine their number of electrons. K plus, what do you think the number of electrons is? It has lost one. That's going to be 18. S2 minus is also going to be 18. Cl minus is also going to be 18. And Ca2 plus is also going to be 18. So they all have the same number of electrons or the same electronic configuration. So they are said to be isoelectronics. So the next term to talk about is allotropes. Allotropes are different structures of the same elements existing in the same physical state. They have different physical properties, but same chemical properties. So don't forget, just the same element, but that element existing in different structures and having the same physical state. Now, for allotropes, the allotropes can either be in the crystalline form or in the amorphous form. The crystalline form is the one that has a particular shape, while the amorphous forms are the ones that are shapeless. They usually exist in the powdery forms. So now, the examples of allotropes of carbon are diamond, graphite, the Buckminster fullerene, the graphenes, while examples of the amorphous forms are the coal, charcoal, and so on. So now, another examples of allotropes are sulfur allotropes. So you have the rhombic sulfur and the monoclinic sulfur, then you have plastic sulfur and the likes. Then you also have allotropes of phosphorus, which is white phosphorus, black phosphorus, and red phosphorus. So they can ask you any of these allotropes. Try to know them before your exam. So now the next one to talk about, let's go back to isotopes again. Sometimes in calculations we need to know the exact amount of the isotopes in terms of the total composition, because imagine I want to do calculation and I have a mixture of chlorine 37 and chlorine 35. I don't know which one to use, but I can decide to determine the average of these two guys to use them in my calculations. So now looking at this guy, how do we determine the average of these guys? So we use what we call relative atomic mass. So let's look at the formula that you use when you are calculating for isotopes. Don't forget, at the end of this class, I'm still going to do another video where I will solve all of your JAMB past questions and WAEC past questions on the topic we have done, so that you use it to understand it better and clearly. If you're here to subscribe to our channel, please make sure you do as we move on with the class. God bless you. So now, so when you want to do your calculation on isotopes, so the formula is relative atomic mass is given as the sum of the masses and abundances, sum of masses and abundances of the elements over the sum of the abundances. Meaning that, let's say I have an element X, and this X has a particular atomic mass, let me just call it M1, and another one with M2, but the abundance of this, let's say it is A1, and the abundance of this is A2. So if I say calculate the relative atomic mass of this guy, so you can say that the relative atomic mass, depending on the number, just sum everything. So that's going to be sum of the masses multiplied by the abundance plus the second one multiplied by the abundance over the sum of the abundances. So we're going to solve various questions on all of this in our next video, where we are going to solve questions generally on atomic structures. But you try and solve this example that I'm giving you up above. So solve for chlorine in this example, and you can see the answer there. So you sum the masses, multiply by the abundances, divided by the total of the abundance, then you get your answer. And that is what we usually use as relative atomic mass for chlorine in any of our calculations. So now that you have understood everything about the introduction to the atoms, let's quickly look at what we call the quantum numbers. The quantum numbers. We have 4 quantum numbers, and what is the usefulness of these quantum numbers? I want to arrange electrons into a particular space. I want to talk about everything about the electron, the location of the electron, the shape of where the electron is located, and all of these things, how the electron behaves. So the behavior of the electron is described by these 4 quantum numbers. The 4 quantum numbers are principal quantum number, azimuthal quantum number. Azimuthal is also known as subsidiary, or it is also known as secondary or angular quantum number. Then we have what we call the magnetic quantum number, and we have what we call the spin quantum number. So when you're talking about the principal quantum number, it is denoted as n. That determines the electronic shells. When you're talking about azimuthal, it is denoted by L, and that represents the shape of the orbitals and talks a lot about the orbitals. While the magnetic quantum number talks about the spatial orientation, how many folds degeneracy do we have for each orbital. We're going to do the calculations, we're going to see. Why the last one is the spin, talking about electron, one electron will face up and one electron will face down. This is how you face. Then when one is up, when one is down, then that is what spin quantum number is talking about. So let's quickly look at the basic calculations and everything you have to know about the quantum numbers. So let me briefly, so that you understand this. Now the first quantum number is called the principal quantum number. Now this principal quantum number is denoted as n. Is denoted as n. So you will see this a whole lot of times. Now they will give you that n is equal to 1, 2, 3, 4, 5, and so on. Now when n is 1, they can ask you which shell is that. So when we're talking about the structure of the atom, we have something like this. So we have the K shell, the L shell, the M shell, and so on, even to the N shell. So all of these shells are determined by these principal quantum numbers, meaning that n is equal, when n is 1, that is talking about the K shell. When n is 2, that is talking about the L shell, the M shell, N shell, O, and so on. So all of these shells are determined by the principal quantum number, and each of these shells carries a maximum number of electrons. So they can ask you that what is the maximum number of electrons found in a shell. So the maximum number of electrons is given as 2n raised to power 2. So what does that mean? How many electrons can I find in K shell? So that means we're going to say if K is equal to 1, that means n is equal to 1. So you can say that would be 2 into 1 raised to power 2 and 2. So that means the maximum number of electrons you can have in L shell, in K shell, is just 2 electrons. So when n is 2, what is the number of electrons I can have? That would be 2n raised to power 2, which is 2 into 2 raised to power 2, and that would be 8 electrons. So the maximum number of electrons I can have in L shell are 8 electrons. And that is what that is talking about. So determining the electronic shell. So they can ask you, what the principal quantum number talks about? It talks about the orbits. You know, I told you this is called the orbits, or the shells, the electronic shells. So now, after you have known about the principal quantum number, let's look at what subsidiary quantum number talked about. Please follow this one after the other, because we'll be needing them to understand some concepts. So now, the second person to talk about is azimuthal. So azimuthal quantum number is also called subsidiary. A subsidiary, you can also call it angular. In some exams, you can put the other names, then you can also call it secondary. So now, for azimuthal subsidiary angular, this is denoted as L. That's the symbol. And this L has a value of n minus 1. So what does it talk about? Azimuthal divides shells into orbitals. So all these subshells are divided into orbitals. So what are those orbitals that we have? So K was divided into a particular orbital, L is divided, M is divided. But let's see how it's done. So this is saying that your L can have a value of, just note this first, L can have a value of 0, 1, 2, 3, and so on. Now, note something. Whenever you see that L is 0, that is talking about the s orbital. When L is 1, that is talking about the p. When L is 2, that is talking about the d. And when L is 3, that is talking about the f. Now, let's bring the two together. This talks about the orbitals. This talks about the energy levels of shells. Now, let's see how this determines this. You can see that L is equal to n minus 1. That's the formula. So now, if I say that your n is equal to 1, what will your L be? L is going to be n minus 1, which is going to be 1 minus 1, and that is going to be 0. That means that L is 0. So when L is 0, which orbital is that? S orbital. So this represents S orbital. That means if you take this and this together, that means this just represents 1s. And you remember, when n is 1, how many electrons can occupy the place? I wrote it the other time. That means you can have 2 electrons. Because if you do your calculation, 2n raised to power 2, that means 1 raised to power 2 will be 1 times 2. That will be 2. So now, if you look at what we have here, when n is 1, L is going to be 0. And that's talking about 1s. And the number of electrons that can occupy s is just 2 electrons. Let's do another calculation. When n is 2, what do you think L will be? L will be n minus 1. And n minus 1 is 2 minus 1. 2 minus 1 is 1. That means that L can be, you know it's 1 here. That means it can be 0 and 1. It's just n minus 1. That is L. So if n is 2, that means L will be 1. So meaning that L goes from 0 to 1. So that will be 0 and 1. So you stop there. So meaning that this is S and this is P. So if you take them together, that means this is 2S and this is 2P. So yeah, do for this quickly. When n is 3, what do you think L will be? L is going to be 3 minus 1, that's 2. Meaning that L can either be 0, 1, and 2. So when L is 0, 1, and 2, that is S, P, and D. And what does that mean? This is 3S, 3P, and 3D. So this shell now has been divided into these orbitals, SPD orbitals. I hope you're following. So that's how you do the calculation. Can you do that when n is equal to 4? What will it be? That means that L is going to be 0, 1, 2, and 3. And what does that represent? That will be S, P, D, and F. That will be 4S, 4P, 4D, and 4F. So just note this for now. We're going to bring everything together and you will see the usefulness. So that is what azimuthal is doing. Now, one thing you need to note is that azimuthal gave what we call, you can watch this over again to just quickly see how I got it. You can rewind, you can take this back a bit. You can take this back a bit to just understand that I got what I just did now. But let's go on so that you can understand everything all together. So now, this is why it's a video. That's why I can pause. That's why I can take it back to understand things clearly. Instead of a class that will just skip and move on and you might not really understand it. But for now, you can. Let me give you something. Let's say, Drew, give this in your answer in the comment section. First question. When n is 2 and L is 0, which orbital am I talking about? A, 2S, B, 2P, C, 3S, D, 3P. So which orbital do you think I'm talking about? Leave your answer in the comment section. When n is 1 and L is 0, which orbital is that? That's number 2. Number 3. when L is 4 and L is 3, which orbital do you think that is talking about? So quickly write that and let me see what your answer is in the comment section to show if you understood what I just finished talking about. But let's go over it again. So now the third one we want to talk about is what we call the magnetic quantum numbers. The magnetic quantum number. Now, when you're talking about magnetic quantum number, it is usually denoted with m sub L. Now, before I talk about that, okay. So another thing that subsidiary talked about was the shape of the orbitals. So you must have had s orbital is spherical, p orbital is dumbbell, d orbital is double dumbbell, and f orbital is complex. So you can know the shape of all of these orbitals. They can ask you in exam, what are the shapes of these orbitals? So let's talk about magnetic quantum numbers. So number 3, magnetic quantum numbers. So when you're talking about magnetic quantum number, what is it saying? It is represented as m sub L. So now, magnetic quantum number has a value of minus L through 0 to plus L. Minus L through 0 to plus L. It talks about the orientation of the orbitals. That means, is the orbital facing that side or is it facing this side? The arrangement, the orientation. So now let's look at the different orientation we can have for different orbitals. So let's look at this question again. When n is 1, what is L? Very good. L is going to be n minus 1. So L is going to be 0, Abi, and that is 1s. So ml is going to be whatever L is, we determine what ml will be. It's going to be, there's nothing like minus 0 plus 0. So ml is just going to be 0. And this simply means that this, you remember 1, 0, this is S, Abi. So that means that this is 1S. So 1S, we only have just one spatial orientation. Just one. So we call this one-fold degeneracy. One-fold. Let's look at another one. When n is 1, when n is 2, what will L be? L will be 0 and 1. We just finished doing that, right? L will be 0 and 1. So L is 0. So when L is 0, ML is going to be 0. Because you can't have minus 0 and plus 0. But when L is 1, ML is going to be minus 1, 0, and plus 1. What does this mean? This one will just be one space. Why this one will be 3 spaces? Now, you must have been connecting now. If this is 2, then this is S, this is P. That means S is only divided into 1, while P is divided into 3. So we call this threefold degeneracy. Threefold degeneracy. Now, let me make this clearer. So let's go over it again. Let's go over the calculations again. Now, in a clearer picture. So in a clearer picture, let's say n is equal to 2. If n is 2, what do you think L will be? L is going to be 0 and 1. Do you agree? Because that will be n minus 2 minus 1, that's 1. So that means it goes from 0 to 1. Then, ML. So if L is 0, so let me do it this way. This represents S and P. So this represents 2S and 2P. So now, ML depends on L. If L is 0, ML is going to be 0. Do you agree? That means that it will only have one-fold degenerate. If L is 1, ML is going to be minus 1, 0, plus 1. And that means it's going to have threefold degenerate. So that means the P is divided into 3, S is just 1. Let's do one more. So you're going to do this yourself now quickly. You can take a pause to do this one. And let me see how you get it. So let's say your n is 3. Oh yeah, take a pause and do it. So if n is 3, what are the values of L? Then what are the values of m sub L? Oh yeah, take a pause and do that. Then play the video to see if you have gotten it. So yeah, let's go by it. So if n is 3, then L is going to be 0, 1, and 2. Don't forget, L always have the value of 0 to n minus 1. L always have the value of 0 to n minus 1. So meaning that if n is 3, that's 3 minus 1, that's going to be 2. So that will be 0 to 2. So that will be 0, 1, 2. And when n is 0, which of the times that's s, p, and d. So meaning that this is 3s, 3p, and 3d. Do you get that? So now let's find the value for n. So if n is 0, ml is going to be 0. Meaning that is just 1 fold degenerate. If n is 1, ml is going to be minus 1, 0, plus. So my phone is off here, my mic is off. So this is talking about if L is 1, then ML is going to be minus 1, 0, and plus 1, because we're taking the value of ML to be minus L through 0 to plus L. So meaning that the P will be divided into 3-fold degeneracy. So now, if L is 2, ML is going to be minus 2, minus 1, 0, plus 1, plus 2. And if you count that, that means it's divided into 5-fold degeneracy. So you can count that. So that's how you determine the values of M sub L. So we have determined the values of n. When n is 3, L is 0, 1, 2. Then when L is 0, ML is 0. When L is 1, ML is minus 1, 0, plus 1. When L is 2, then ML is minus 2, minus 1, 0, plus 1, plus 2. So you can see that the S is just 1, P is divided into 3, and D orbital is divided into 5. So that's what that part is talking about. So can you try for when n is 4? Determine the value of L and determine the value of M sub L. So when L is 4, what are the values of L you are going to have? What are the values of M sub L you are going to have? So that's what that part is talking about. So don't forget that the principal quantum number is represented with n, is denoted with n. Then the azimuthal formula is it goes from 0 to n minus 1. So that's how you determine the L, which is azimuthal. Then for the M sub L, it's going to go from minus L. So M sub L is going to go from minus L through 0 to plus L. So that's what we are just writing out again. So knowing those three, then you can determine the n value, the L value, and the M sub L value. So the last one is the spin quantum number. So the spin quantum number talks about the spinning of the electron on their axis, and it always has the value of plus or minus 1 over 2, meaning that when it is plus 1 over 2, electron spins up. When it is minus 1 over 2, electron spins down. And that's why you always have one electron up and one electron down in an orbital. So you need to understand that. So there is no way you write configuration and the two electrons face up. That would be wrong. So the one electron will be up and one electron will be down. The one that is up is represented with plus 1 over 2, while the one that is down is represented with minus 1 over 2. So now, after all of these things we have talked about, let's now use a very big table to represent everything all over again, to now see if you have understood what we have said so far. So the first column of the table, the first column represents the shell. So the next one represents the principal quantum number, then followed by the azimuthal quantum number, which takes the value of 0 to n minus 1. Then followed by the magnetic quantum number, which is M sub L, which takes the value of minus L through 0 to plus L. So you need to note that. So then there's a general formula I wrote there. You might just note that in your notes. The general formula is M sub L is equal to 2L plus 1. 2L plus 1. I'm still going to explain that as we move on. So the other part of the column is M sub S, then the orbitals, then the maximum number of electrons you can have. So for the first shell now, when you have K, then that means n is going to be 1 for K shell. Then what will be the values of L if n is 1? Then you know it's going to be 1 minus 1. So that will be 0 to 0. Because 1 minus 1 is 0. So that means L is just going to be 0. And when L is 0, that represents s orbital. Then if L is 0, then m sub L is going to just be 0, because you can't have minus 0, 0 and plus 0. So m sub L is just 0. So meaning that it is only divided into one, just one shell. That's what you have for m sub L. So for m sub S, electrons inside will just spin up, and if there are 2 electrons, they will spin up and down. So they always have the value of plus or minus 1 over 2. One electron will spin up and one electron will spin down. So if you look at the orbital now, that is 1s orbital. So what will be the maximum number of electrons you can have in s orbital? That's just 2. She get. So that's what that part is talking about. So the maximum number of electrons is given as 2n raised to power 2. So meaning that if n is 1, then 1 square will be 1, 2 times 1 will be 2. So the maximum number of electrons in K shell is 2 electrons. We are just using this table to summarize everything. So when the shell is head, that is n will be 2. Then that will be 2 minus 1, that's 1. That will be 0 to 1, that's 0 and 1. Do you understand that? So if n is 2, then L will be 0 to n minus 1. 2 minus 1 is 1. That means the values of L will be 0 and 1. And 0 represents S and 1 represents P. So when L is 0, m sub L will be 0. When L is 1, m sub L will be minus 1, 0 and plus 1. And we will have 3 degeneracy there. So we have 1 fold and we have 3 folds degeneracy. So the value will always be plus or minus 1 over 2, because 1 electron will spin up and 1 electron will spin down. So that will be 2s and 2p, because L is s and p. So that's 2s and 2p. So what will be the maximum number of electrons? 2 electrons will be in s and 6 electrons will be in p. So that means the maximum number of electrons will be 8 electrons in total. Or you can just say 2 raised to power 2, that's 4. 4 times 2, that's 8. So you can determine that. So for M shell, what will be the N? 3. Then what will be the values of L? That's going to be 3 minus 1, that's 2. So that will be 0 to 2. So that will be 0, 1, and 2. Do you get that? So you can try that on your own. Let's see what you're going to have. Try that quickly. Try all the things I've talked about again. You can practice that. So get the values for all of those things I've talked about and deal with them and complete the table. So do for when n is 3 and do for when n is 4. Now this is the formula I wrote up there. I say ml is equal to 2l plus 1, which means I can determine the number of fold directly. You know, when L is 2, it's going to be minus 2, minus 1, 0, plus 1, plus 2. That means it will be 5-fold degenerate. So you can just put it in the formula to determine that straight. That means 2 times 2, that will be 4. 4 plus 1, that's 5. Do you get that? So M sub L can be determined using that formula, 2L plus
so
1.
Now that you know about the quantum numbers, let's quickly talk about the rules that guide electronic configuration. What are the rules that guide electronic configuration? So there are 3 major rules that guide electronic configuration, how we can arrange the electron in the orbitals. So don't forget the definition of orbital. Orbital is defined as the region of maximum probability of finding an electron. So that location where you can find an electron is called an orbital. So quickly, let's look at the rules that guide electronic configuration. The first rule is called the polar exclusion principle. The first principle is called polar exclusion principle. The second one is called the Hofbauer rule, and the last one is called the Horn's rule. So when you're talking about polar exclusion principle states that no 2 electrons can have the same set of values for the 4 quantum numbers. That means that no 2 electrons can act in an identical manner. Even though you are from the same parent, you cannot behave exactly in an identical way. So for example, now if I say that from what we just finished, if I have 1s2, there are 2 electrons here. Let's determine their principal quantum numbers. So the principal quantum number for the first electron is going to be 1. Then what will be the azimuthal? Since it is S, that's going to be 0. You remember, we said when L is 0, that is S. When L is 1, that is P. When L is 2, that is D. When L is 3, that is F. That's what we just finished doing. So now,
what would be the ml? Since it is s, it will only have one fold degeneracy, abi? But now there are two electrons here, and we said something that one will either spin up and one will spin down. So looking at that now, that means that my m sub s is going to be plus 1/2 for 1. For the second electron, it is also occupying the same place, which is n is 1, l is 0, then ml is also 0, and that is one fold. But the m of s for this is going to be minus 1/2, meaning that as this one is spinning up, the other one will be spinning down. So if you look at this set of values, even though they occupy the same principal quantum number, they occupy the same orbital, they have the same spatial orientation, but their spinning is different. So Pauli exclusion principle states that no two electrons can have the same set of values for the 4 quantum numbers. So you need to note that. So the next one is called Aufbau principle. Aufbau principle talks about the arrangement of electrons in the orbitals, and it states that electrons are fed into orbitals of lower energy before you start filling orbitals of higher energy. So what does that mean? So if you look at this configuration, the arrow shows the one you have to fill first. So you have to fill 1s before you fill 2s, before you fill 2p, before you fill 3s, before you fill 3p, before you fill 4s, before you fill 3d. So that's how you go. If they ask you why do you have to fill 4s before filling 3d, it's because the energy of 4s is lower than that of 3d. That's why you have to fill it first, and that is what Aufbau has said. You have, if you are writing electronic configuration. So for example, now let's say what I have is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d. Now just draw your arrows like this. So you can write configuration for any element on the periodic table. 6s will still be here, and so on. So you still having 6d, then you still have 6p, then you still have 7s. So now if you look at what you have here, if you're filling the electronic configuration, you have to fill 1s first, followed by 2s as the arrow goes, then followed by 2p, then followed by 3s, then followed by 3p, then followed by 4s. Can you see? Then followed by 3d. So you will see that 4s has to fill before 3d, meaning that 4s is of lower energy than 3d. So if they give you an element that you should write the electronic configuration, let's say you are given nitrogen and the atomic number for nitrogen is 7, and they say write the electronic configuration, that means this is going to be, the first one you pick is 1s, and remember the maximum number of electrons in s is 2, so that will be 1s2, followed by 2s, that will be 2s2, followed by 2p, that will be 2p. P can take 6 electrons, so that will be 3. Do you get that? So if you add all of this together, that's 7 already. So you have written for that. Let's say I want to write for calcium. So what will it be? That's going to be 1s2, followed by 2s2. Calcium is 20, followed by 2p6, followed by 3s2, followed by 3p6. Is that complete already? No. Followed by 4s2. So if you look at it, this is 2 plus 2 plus 6, that's 10. Plus 10, that's 20 in total. So this is the electronic configuration for calcium. But I told you to know hydrogen to zinc on the periodic table, which is the first element to the 30th element. So I want you to take it as an assignment. Write the electronic configuration for this guy and note something about copper and chromium. Note something about them. You can remember this. School T, V, Krum, Mi, Fe, Koni, Cuisine. Those are the next 10. If you know from hydrogen to calcium, which is 1 to 20, this is from 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So these elements are very important for you to remember them. School, Tivin, Krumi, Fe, Koni, Cuisine. So that helps you to remember them. So school TV Kurumife Koni Cuisine. It's more from a Yoruba language. So, but you can say it's just like I'm speaking Japanese to remember what I need to remember. So school TV Kurumife Koni Cuisine. So now from what we have here, you can be asked to write the electronic configuration of these guys. Let's say I want to write the electronic configuration for scandium. You know argon. Argon has electronic configuration of 18. So you can just put argon like this, so that you don't have to write everything. And for 18, that means that's 3D. You remember, argon represents this. The configuration for argon is 18. So that's going to be 1s2, 2s2, 2p6, 3s2, and 3p6. If you add all of this together, that's 18. So instead of rewriting this over and over, I can just put argon, meaning that putting argon here, I'm representing all of this guy. Then after 18, after 3p6, which one is next? 4s2. And you remember, scandium is this, 21. So meaning that 2 plus 18 now makes 20. So it remains 1. After 4s, then you feel 3d1. So that's scandium. Do the same thing for titanium. That's going to be argon, 4s2, 3d2. Do the same thing for vanadium, but note something about chromium, because it can test you in any exam. Chromium is going to be 4s1, 3d5, not 4s2, 3d4. The reason is that when your orbital is partially filled, I'm not using this to represent the, I'm just explaining something. When it is partially filled, it is more stable than when it is incompletely filled like this. This is more stable. So this guy prefers to be stable. That's why the D will be partially filled first. So you will have something like this for that D now, because D is supposed to be 5. 1, 2, 3, 4, 5. You know, after the 4s1, so you moved 1 electron because it should have been 1, 2, 3, 4. You now moved 1 electron from here to here so that it can be partially filled, so it will be stable. That's why the configuration is this. So if you pick this in exam, 3d4, you are wrong. So the best to pick is this. When they say write configuration for chromium, check for copper too. Do the same thing for copper, and let's see how you write the configuration. So you must always take note of chromium and copper whenever you are writing the element, the configuration of these so-called transition elements. We're going to talk about them with time again. So now, that is it about Haber principle. You have to fill orbitals of lower energy before filling that of higher energy, and energy increases as you go down that place. So now the next thing to quickly talk about is Hund's rule. Then we end the class. So for Hund's rule is called Hund's rule of maximum multiplicity. It states that when you are filling electron into degenerate orbitals, degenerate orbitals are usually orbitals of the same energy. So when you are filling electrons into degenerate orbitals, electrons are shared singly before pairing occurs, before you start pairing them. What does that mean? Look at what I'm saying. Look at this nitrogen, for example. If I want to feed the nitrogen into orbitals, you're now going to have 1s2, 2s2, 2p3. So Hund's rule is stating that when I get to degenerate orbitals, that's this p now is divided into 3, so they are assumed to have equal energy. So now, if I want to fill the 3 electrons, I should not fill 1, 2 first and leave this empty. Then I'll fill this. This is wrong. So I have to fill it this way. So when I want to fill the P, I have to first fill 1, 2, 3. Singly. Even if there's anything left, I will not start pairing. That's what it's saying. Let's look at another element. Fluorine. Let's say, let's just say oxygen. The atomic number for oxygen is 8. So that means oxygen is going to be 1s2, 2s2, 2p4. So when I get to this place, if you do this, 1, 2, 1, 2, this is wrong. The best way to fill this is you start singly 1, 2, 3, then 1 is left, then you now pair the last one. So this is correct. So Hund's rule is stating that when you are filling the degenerate orbital, such as like your p orbital, your d orbital, your f orbital, You have to fill the electron there singly before you start pairing, and that is what it's talking about. So now that you understand all this, they can now ask you a question. They can say that for nitrogen, how many unpaired electrons will it have? Look at it, 1, 2, 3. So it has 3 unpaired electrons. For oxygen, how many unpaired electrons does it have? You can see 1, 2. So it has 2 unpaired electrons. So in order to show that you understand this, how many unpaired electrons do you think fluorine will have? Oh yeah, let me see. How many unpaired electrons do you think carbon will have? So carbon is 6, fluorine is 9. So tell me their number of unpaired electrons. So that brings us to the end of atomic structure. Answer the following questions that I'm going to upload. And after this, leave your answers in the comment section. So after this, we'll be moving on to the next topic, which is periodicity. Please make sure you have watched this video over and over, understand the concept clearly, and try to subscribe if you're yet to subscribe. Share it with your friends so that you help us to build the algorithm. And we're going to start solving questions on everything in the next class. So in my next class, I will upload a video where I will solve all the past questions on atomic structure in the next class. So don't forget to subscribe so that you get updates on the subsequent videos. So I'll see you in the next class. Bye.